Not. Okay. Let's start with chapter 4, differential relations for fluid flow. Okay. Before we start, let's just look quickly at what this chapter is all about. Well, the first part is about the acceleration field of a fluid. Then we're going to do the differential equations for mass conservation, linear momentum, angular momentum, and energy. Then boundary conditions for the basic equations, followed by the stream function, vorticity and irrotationality, frictionless and irrotational flow, and then some incompressible viscous flow examples. So that is an overview of what we're going to do in this chapter 4. Okay, so chapter 4 is differential relations. Now, what is the background? Why are we interested in differential relations? Well, if we want to analyze fluid flow, then there are actually two approaches that can be followed. The first approach you did in chapter 3 last year. Chapter 3. And in chapter 3, you did specifically integral relations for a control volume. Integral relations, specifically for a control volume. And in that, you were interested in the gross effects. The gross effects, the total effects. You were not interested in the small details. So, for example, you could look at a rocket with a nozzle like that. And with that approach, what you did is you selected a control volume, typically around the body that you were interested in. And that body can maybe be a pump with some pipes going in and some pipes going out. And you can select the boundary condition around the whole system of pumps and pipes and stuff like that. Okay. So in that, maybe you were interested in getting the velocity of the rocket as a function of time with certain things specified. For example, maybe the mass flow rate of the combustion, and maybe you were interested also in determining the outlet velocity or the velocity in the throat of the rocket. Okay, so here's the rocket. Okay. And in most cases, what you did is you had a one-dimensional approach. So, for example, when you looked at that throat, the result of that assumption would be that if you solve the velocity, that the velocity would be uniform throughout that throat. So that would be the velocity at the throat. So the velocities are not equal to 0 on the walls. You're not interested in the details, just the gross effects. Okay, so that is what you did in that chapter. Then at the same time, if you typically would look at some of the equations, then the equations had the following format. They were integral equations, so therefore they've got an integral in it, control volume, the integral over the control volume of typically d rho dt, the volume. Please take note that the V is a V for volume, because in many cases we use V for velocity. Okay, that would then be equal to, that plus the sum of all the terms of rho, area, and the velocity out minus the sum of all the terms of rho, the area, and the velocity in would be equal to 0. Do you remember that equation? So that is the typical equation that you could use if you want to solve something by use the continuity equation. In many cases, the continuity equation on its own is not enough. You also had to use not only the continuity equation, but also the linear momentum equation. And take note, it's an integral continuity equation, it's an integral linear momentum equation, a linear angular momentum equation, and then an integral energy equation. So those were the equations that you've used in chapter 3 to solve practical problems with. Okay. Now, let's look at chapter 4. Chapter 4, that is the second approach that can be used to analyze fluid flow problems. First one, we use integral relations. Now we're going to use differential equations. Differential equations, okay. And where previously we were interested in the gross effects, now we are interested in the detail effects. Okay, the small detail. So, again, when we look at this rocket, at the throat of the rocket, now we are interested in what happens in a small control volume. Okay. We want to know what happens in a small control volume so that it is possible for us to solve the velocity, which is typically going to look something like that. The velocity through the throat, which is now a function of the radius of the throat. Okay, and where previously our equation for continuity looked like that, our equation for continuity for a differential equation is going to look like this. d rho dt plus ddx of rho u is now equal to 0. And that would now only be the one-dimensional equation, not the three-dimensional one. So the one-dimensional equation. Okay, so this is now a differential continuity equation. And what we are also interested in many cases, that is not enough. We can't only use that equation to solve problems with. If we want forces or heat transfer or work, we also need to solve the other two equations. So there's also going to be a differential equation for linear momentum, for a differential equation for angular momentum, and a differential equation for energy. Okay. 4 different equations. Differential equation for continuity, one for linear momentum, one for angular momentum, and one for energy. Okay. Okay. Now it is very important for us, or for engineers, and specifically when you're going to do the next course in CFD, to know, firstly, where does it come from? Where does these equations come from? What are their limitations? And or assumptions that were made in the derivation of the equations. And there are 2 things that you can use it for. The one is, we are going to derive a few analytical equations. So it is possible to take these differential equations And in some cases, if you make lots of assumptions, and if the geometry is simple, like for example, the flow through a channel, or flow through a pipe, or a flow between two in a concentric cylinder, those cases can be solved analytically. So those equations are very, very important to us, and they've got practical applications. So there's a category of problems which can be solved analytical, and in most cases they are called classical problems. In many cases it is really going to test your mathematics in many cases to solve those differential equations. Okay. So we are going to keep it very simple and just solve a few of them just to show to you in principle how it is done and how it can be done. So that is the first part of the problem. The second part is that you're going to use all these equations to solve these equations numerically, and that you're going to do in the CFD course, the Computational Fluid Dynamics course. Okay, so that is the background, all the background, so that you understand how everything fits together and why you need to do this work. Okay, it is not so exciting, I must say. Okay, so it's not so exciting, but the other work that we're going to do is much better, but this part is not really so nice. Okay. The first part is paragraph 4.1 in the textbook, where we're going to look at the acceleration field of fluid. So acceleration. Okay, we are interested in acceleration. Why acceleration? Because if we have the acceleration and the mass, then in many cases we've got the forces. Okay, so that's the reason for it. Okay, and what you already did last year is you have defined the velocity vector. And the velocity vector, typically in an RT coordinate system, can be written as u, which is a function of x, y, z, and t, plus v, which is also a function of x, y, z, and t, plus w, which is a function of x, y, z, and t. So that is in general how you've defined and used the velocity vector last year. Now in many cases, if we have for a flow field the velocity vector, then we sort of have the solution. Okay. In many cases, it's very, very difficult to get that velocity vector. Okay, but in some cases it is known, and if you have it, then you can consider the flow field solved. So that is very easy. Obviously, this is done in a certain coordinate system, and the coordinate system that is being used, or can be used, is XYZ, with the unit vectors I, J, and K. And if we look at this velocity vector, then its components are U, small v, and W. So that is the components of the velocity vector. And this velocity vector is in an Eulerian coordinate system, Eulerian, which means that our frame of reference is standing still, it is not moving. Okay. It is not a Lagrangian one where you would sort of follow the particles of the flow. So this is an Eulerian coordinate system. Okay, now to write Newton's law for an infinitesimal fluid system, we need to calculate the acceleration vector field A. The acceleration vector field A, which is equal to dv dt, or in terms of the three velocity components, can be written as du dx in the I direction plus dv dy in the j direction plus dw dz in the k direction. So it's the time derivative of the velocity field. The problem we have is that each one of these velocity components, each one is a function of x, y, z, and t. Okay. So we should actually, just to make it more clear, write the acceleration as du, which is a function of x, y, z, and t, dx plus dv, also a function of x, y, z, and t, dy plus dw, which is a function of x, y, z, and t, dz. And let's call this equation 1. Equation 1. And because the velocity component is a function of x, y, z, and t, we have to use the chain rule to get the acceleration. Okay. So let's first look at this first term. So we're going to do it for each one of the terms separately. If we look at the first one, then du of x, y, z, t dx is equal to partial du dx multiplied by dx dt. Okay. Du is a function of x, so du dx multiplied by dx dt plus the next term, partial dv dy multiplied by dy dz, dy dt plus du dz dz dt plus du dt multiplied by dt dt, and the two dt dt's are equal to 1. Chain rule. Is that right? Did I make a mistake somewhere?
The second partial, so the v is actually right there was the v
Oh, sorry, this one. Yeah, sorry. Thank you. Okay, do you agree? The chain rule, just write it out. And now, by definition, the x dt, what is the x dt equal to? The x dt is equal to the velocity component in the x direction. Dy dt is equal to v, and dz dt is equal to w. You agree? So therefore, we can write this as du, which is a function of x, y, z, and t, dt is now equal to the acceleration in the x direction, which is equal to partial du dt plus u multiplied by partial du dx plus v partial du dy plus w partial du dz. Any questions? Okay. Or we can say the acceleration in the x direction, which is equal to du dt in general, is equal to partial du dt plus the divergence of the scalar u, which we also call the grad of u. So this is called the divergence the two terms together would be the divergence of the scalar u, or it is called the grad of u. Okay, now remember, we've done the chain rule only for the first term. Okay, we also need to do it for the second term and the third term. Okay. So do the same for the other two terms. dv dt is a function of x, y, z, t is equal to the acceleration in the y direction is equal to partial dv dt plus u partial dv dx plus w partial dw dz. If we go and do the same for the second term. Or we can say it is equal to the partial dv dt plus the grad of v. Okay, so that is for the second term, that term there. Still need to do the third term. So for the third term, dw xyzt of dt is equal to partial dw dt plus the grad of w, the velocity in the z direction. Okay, now let's make all three these terms a little bit neat and write them together. Then we can say the acceleration in the x direction is equal to partial du dt plus the grad of u. The acceleration in the y direction is equal to partial dv dt plus the grad of the velocity vector v, and in the z direction it is equal to partial dw dt plus the grad of w. Okay, and what we're going to do now is we sum it as one vector. So these three terms is the acceleration vector a, then equal to dv dt, the velocity vector v, in its three component directions, u, v, and w, plus the grad of the velocity vector v, the divergence of the velocity vector v. So that in general is the acceleration, if we write it in a very compact form. Okay. The acceleration has two terms. The one term is called the local acceleration, and the other term is called the convective acceleration. The local acceleration and the convective acceleration. Okay. We didn't finish all the work that I wanted to do today, but we will continue with the next lecture. So in general, just to summarize, we've started with the differential relations, motivating the reasons specifically why we are interested in these equations. Then we started with the derivation of acceleration, starting with the velocity vector, using the chain rule, and then adding all together in a very short format and writing the acceleration like that. Okay, ladies and gentlemen, thank you very much, and then I'll see you again with the next lecture.